I want to talk about a question that doesn't get asked enough by roboticists. What is the best robot embodiment for a given manipulation task? We spend a lot of time making robots smarter, with bigger datasets, better algorithms, and more capable policy architectures. But if you think about it, it's the robot's embodiment that enables or constrains what tasks the robot can perform well. For instance, you can collect as much tossing data as you want, but if your robot embodiment is far from optimal, it might toss itself too. So let's frame this problem more concretely. Given as input target and effector motion and some reward function, our goal is to generate complete robot embodiments for the task that achieve high reward. Here, by complete robot, I mean everything, including geometry, kinematics, inertial properties, as well as how it moves with the controller. We call this problem motion-conditioned robot co-design. And today, I'll tell you about our attempt at tackling this problem in one unified framework called Transformer-Transformer, a unified model for motion-conditioned robot co-design. It has 3 parts, and you have until part 2 to figure out the pun in the name yourself. With that, let's dive into part 1, a unified robot representation. If we want a model to co-design any robots, the networks need a common language that span across diverse robot embodiments. So we create robot tokens, a unified robot representation. We call it unified because we've designed it to tokenize any robot, giving tokens that can be used as inputs or outputs to neural networks. So, given a robot like this quadruped manipulator, we'd parse all of its embodiment's attributes into a few token types, including links, joints, and motors. We also include all of the robot's motor states, link states, joint states, and actions too. So we have robot embodiment tokens and robot dynamic tokens. This means robot token is complete because it includes everything about the robot's embodiments and its dynamics. Robot tokens is also flexible. It can handle arbitrary degrees of freedom and connectivity using token IDs. Here, tokens use IDs to point to each other, so joints, for instance, know which 2 links they connect. Robot token is also consistent. The tokenizer does a lot of pre-processing to reduce redundancy, such as by storing inertial and transform data in a consistent frame. The upshot of all this is that our tokenizer can turn any robot into a sequence of embodiment and dynamic tokens, whether it's a biped with complex linkages, a dexterous hand, or a full-blown humanoid. Now the question is, what can we do with these tokens? That brings us to part 2, a unified architecture called Transformer-Transformer. We call it unified because, as you'll see, one model can have different functionalities. As for the pun, the first transformer refers to robots whose embodiments can change, while the second refers to the self-attention architecture. More technically, the model is a diffusion transformer that is trained on robot tokens. Since it's a diffusion model, noise is added to all input tokens except for the conditioning tokens. So for each token, we'll add in that token's ID embeddings before passing it through the model to predict the denoise tokens. Now here's the key insight. You can train this model with different masking schemes to get different functionalities. This means one transformer can wear many different hats. For instance, it can act as an unconditional generator of robot embodiments. Here, the conditioning input is nothing, which means the diffusion model starts from random Gaussian noise with no conditioning information. And the output are complete robot embodiments and their states. Visually, it looks like this. Starting with Gaussian noise, you iteratively run the model to denoise the tokens until you get a denoised robot. And since this whole process is stochastic, if you run it again, you'll get different robots each time. Here, we tried training on different robots from Mujoko Menagerie and found that in a single transformer, you can diffuse out diverse robots, from fixed-based arms to quadrupeds to humanoids to dexterous hands. Our model can also wear other hats. It is also a cross-embodiment controller. It takes as input the target trajectory, the current robot states, and diffuses out the action. We call this control policy embodiment aware because it is also conditioned on the embodiment representation. And this is crucial to help generalization because the control policy is given the complete embodiment information. This means if you run the policy on a robot with different link inertias, smaller joint ranges, or different motor gains, the policy will be able to adjust its control strategy accordingly because it is conditioned on the complete robot embodiment. So we tried behavior cloning whole body control using data from RL experts, and here's what the resulting behavior cloned whole body controller looks like. Notice that these quadrupeds have very different designs, spanning continuous variations like link dimensions, as well as discrete variations like degrees of freedom, knee direction, and whether the leg has a linkage or not. And not surprisingly, larger models do better. And it'll be interesting future work to revisit this with the latest and greatest distillation techniques to make smaller models perform better. So, with these different functionalities under the same model, let's revisit the original motivating problem. What is the best robot embodiment for a given manipulation task? In other words, conditioned on a manipulation task, could we generate robot embodiments that achieve high rewards? This brings us to the third part, dynamics self-guidance, a unified dynamics training objective. And here, we call the training objective unified because it prepares the model to zero-shot optimize unseen rewards at inference time. Let's see how. Given as input the target motion trajectory and a reward function to optimize, the model must output an optimized embodiment. The key challenge here is how can we generate high reward embodiments, especially since the model was never trained on any rewards. Here's the trick. We can use the input reward function to turn the model's own embodiment and dynamics prediction into a pseudo reward prediction. With this reward prediction, we can simply ask the model to generate lots of robots in parallel, predict the reward for each of them, and then return the best one. And this works because we're essentially doing best of n sampling. Imagine that this is a slice of the optimization landscape. As long as we sample enough and then return the best one, we'd likely get pretty good candidates. But could we do better? What if we can take the gradient of the optimization landscape to nudge samples to higher rewards? Let's see. Recall, at each diffusion time step, the intermediate noisy tokens are a function of the embodiment tokens. This means that the pseudo rewards are also functions of the embodiment tokens. So for differentiable reward functions, we can take its gradient and then incorporate it back into the diffusion process, which pushes samples towards higher rewards. With this gradient, we're asking the model to consider how to change the robot to increase the reward. And since the network uses its own dynamics predictions to steer itself, we call this procedure dynamics self-guidance. When we train the model for this task, we use a long context with time steps into the future. This forces the model to learn long-range dependencies between robot embodiments and robot dynamics over extended time horizons, which ultimately leads to better reward predictions. So, does it work? Let's start with this tossing task, where this randomly generated quadruped would fall over. When we asked our model to generate a robot for this task, it combined many different tricks to make the robot more stable for this dynamic motion, such as lowering the center of mass and increasing the support polygon. And it did all this as a result of trying to maximize the tracking reward, which it has never seen before during training. For the same trajectory, we can also ask the model to optimize more terms, like minimizing torque. This made the robot smaller and therefore lighter, while still being able to do the task. This reduced the average torque usage by 32%. And by adding another reward term, we're essentially changing the optimization landscape. This would also change what the best robot is for the task, because now the model must balance between these two objectives, sacrificing a little bit of tracking performance to use less torque. And our model is able to make this trade-off, demonstrating that after you train on embodiment dynamics modeling, you can optimize unseen reward functions. In other words, the model can zero-shot optimize rewards. Now, back to this landscape. You'll notice how there are actually multiple peaks. These complex landscapes are common in robot co-design problems. And despite this challenge, our model is able to generate high reward designs from different peaks. This is because the model's diffusion training enables diverse, multimodal embodiment generations at test time. And we've seen how changing the reward changes the landscape. Changing the target motion also changes the landscape. Here, when we condition on different trajectories, we indeed see that our model produces different robots, each specialized for a single motion that it was conditioned on. But wait, let's take a step back. We don't actually want to optimize robots specialized for just one motion. We actually want to optimize for manipulation tasks, which are much better captured by a distribution of motions. So, How could we do this? It turns out we can directly tackle this by composing diffusion models. At the high level, if we have one model that's optimizing for tossing and another optimizing for chopping, we could get a model optimized for both tossing and chopping. So to test this, we took the publicly available bimanual dishwashing demos from Uni, took out 26 validation trajectories, extracted the n-effector motion, fed it into transformer. The model would then generate robots that are optimized for all the trajectories that we gave it, helping us navigate the large design space of both discrete choices like different spine designs, as well as continuous choices like arm dimensions. After generation, the same unified model is also the cross-embodiment controller used to validate the generated robots. Essentially, what we've done here is input a dataset of human demonstration trajectories and got out a robot simultaneously optimized for all those motions for a task as complex and long horizon as dishwashing. This demonstrates we can zero-shot optimize for a manipulation dataset with multi-trajectory optimization. We also have quantitative comparisons of our approach against baselines. The evaluation procedure is that we'll generate a robot for a target trajectory and a reward function. We'll control it to track the target trajectory, then we'll report the achieved reward. Here's the random baseline, which of course does really poorly. We also have a CMAES baseline, and since it works by rolling out robots in simulation and then returning the best one, we can allow it to try more candidates to improve performance, shown here in different shades of orange. Now here's transformer. You'll notice how you get even better performance than CMAES while taking much less time. We can also let our model sample more designs before returning the best one, taking more time to get better performance. However, even when our model uses 128 samples, it finishes in less than a second. Why is our formulation so much faster? There are two reasons. The first reason has to do with using GPUs instead of CPUs, which can efficiently parallelize over the number of samples. The second is more interesting. Typically, dynamics models are sequential autoregressive models, predicting one time step at a time. In contrast, we have a non-autoregressive diffusion architecture, so performance over an entire episode is evaluated in parallel as opposed to sequentially. These two factors of parallelization multiply, leading to the speedups that you see. Up next, using dynamic self-guidance in green, we found that this gradient information was useful to squeeze out some extra performance. However, using dynamics guidance means the model now must perform both the forward pass and the backward pass. Although this doubles the optimization wall clock time, it's still 4 to 16 times faster than CMAES. Now, these results are for a reward that only has one term for tracking precision. But we see the same pattern for other reward functions involving velocity, torque, size, and weight regularization, even though the model has never seen any of these reward functions. They also hold beyond single trajectory optimization, extending to multi-trajectory optimization too. Here, the speedup thanks to parallelization is even larger. And beyond fixed-based arm results on ViperX, we also have results on quadruped manipulators and bimanual mobile manipulators, demonstrating the method's applicability to diverse design spaces. Here, we want to highlight one key result in bimanual mobile manipulation. To optimize these robots for 26 dishwashing demonstrations simultaneously, our model runs 3 hours faster than the CMAES baseline. And to achieve this performance, it reasoned by itself for up to 60 seconds, using more inference compute to get a better design. The upshot here is that transformer can generate better robots when allowed to search over more inference seeds, demonstrating test time scaling. Finally, we wanted to stress test the system to see if its optimized designs can be fabricated with real hardware. For these real-world experiments, we chose flinging for cloth unfolding. This practical manipulation task is not just challenging because it involves dynamic high-velocity flings, but also because it demands robustness to mismatch physics, from cloth friction to aerodynamic drag. When we tested this task with the original Aloha design, we found that even with a lot of effort, it struggled to even track the trajectories. In contrast, when we asked transformer to optimize the design, it came up with this. Notice how the lengths are longer than the original. It's long enough to kinematically reach targets over the flinging motion, but lightweight enough to be supported by Aloha's smaller motors. It's also mounted the arm upside down, enabling a more energy-efficient underarm swing as opposed to an overhead fling. These design choices enable good tracking over the entire flinging trajectory, leading to a fully unfolded cloth at the end. Quantitatively, we saw a 73% reduction in tracking position error, along with a 30% reduction in maximum joint speed. These results demonstrate that our optimized designs are manufacturable and their gains robustly transfer to real hardware. So, in summary, we propose Transformer. It's one model that can wear many hats, including cross-embodiment control and robot co-design. The architecture is a non-autoregressive diffusion transformer that diffuses out embodiments and dynamic robot tokens simultaneously. This formulation enables diverse generation, parallelized evaluation over time and samples, as well as zero-shot multi-trajectory optimization through composition. It achieves this by training on generic dynamics modeling objectives, allowing it to zero-shot to many reward functions. Altogether, Transformer rethinks robot co-design for manipulation as a three-part process. It starts with demonstrations of how the end effector should move. These motions are then optimized by our model to maximize the specified reward function, and it will explore large design spaces with reward-guided diffusion. This process generates complete robots that it can self-validate by directly controlling them. This process puts the manipulation task front and center. Instead of starting with the robot, then asking what tasks it could do, our framework flips this question on its head. Starting with the tasks themselves, then asks what is the best robot for the given manipulation tasks. Please check out our paper and website to learn more. Thanks.